Alright, let's get started with today's set of problems. First one that we're going to go through is threesome. uh, Immature brain. Anyways, number 15, threesome. Given an integer of array nums, return all the triplets. Nums I, j, and k such that I is not equal to j. Basically, that they're all unique from each other, and that all three of them added together equals 0. Notice that the solution set must not contain duplicate triplets. So I've actually done this problem before, but it has been quite some time. The idea is actually pretty similar in pattern to yesterday's problem, which was, or one of yesterday's problem, which was longest substring without repeating characters. In the sense that it still uses a sliding window pattern. If I can type. And the idea is that because you have three numbers, you really have like an exponential number of combinations that you can have. However, you can limit actually the sort of number of operations that you have by quote unquote pinning one of those values at a time and then searching the rest of the array as a sliding window in order to solve it. So the approach is as follows, as far as I can remember. For each value or num in nums, pin the number on or pin the current index for each number in the sliding window between the number's next value and the end of the array. So basically we create a sliding we create a sliding window between the next value after our pin as well as the end of the array. Check to see if the combination is first unique and then adds up to 0. If true, then add combination to array or to list. If not, shrink the sliding window. I guess it's not really a sliding window. It's more of a, I guess the 2 pointers. So I sort of misspoke there. It's not a sliding window pattern like the problem yesterday. It's more of a 2-pointer approach. It's a 2-pointer because we're not really sliding any window. We're just moving these 2 individual pointers. And we don't really care about the middle part as much as we would for something like a sliding window approach. The question really is for this uniqueness. That is something that I'll have to think about a little bit more. Let's see. No, there can be I is not J, I is not K, and J is not K. Oh, we just can't use the same number twice. Sorry, okay. That makes a lot more sense. Whoops, okay. Yeah, that was a mistake. So the combination, check if the combination is first unique and then adds up to 0. In that case, can we establish uniqueness without checking all of our existing combinations? I think the answer to that is yes. But we need to do something else first. And that something else, I believe, is sorting. The idea is that, and the reason why I go to sorting is that when we move the pointers up and iterate through the array, by having a sorted list rather than an unsorted one, then we can't use the pin for the same combination twice. Because if we have a number like -1 here, could have another -1 here, but then we only have access to one of the other -1s. So we can't necessarily have the same combination as before of like -1, -1, 2, because there's only one -1 that we have, and that's our pin there. So we sort of, by sorting the array, we sort of get rid of that possibility to a certain extent of using the same combination in that way. So because we are pinning through each one, so iterating over the numbers is O of n time, even though we might not necessarily go through all of them, but we could. Technically, I think we probably should stop beforehand, but we'll get to that. And ultimately, it doesn't really change the fact that this is a linear time sort of scan, because we have to go through most, if not all, the elements in the array. Then for this 2-pointer sort of movement, we sort of go until they cross. That will go until, so this will be O of n, or this will be, I'm going to put it down here just to make it more visible. This will be n minus 1 plus n minus 2 plus dot dot dot, and so on and so forth, because we're shrinking it until we get to 1. And that's a good question. I'm not sure as to what that sums up to. This is a monotonically decreasing one. I'm tempted to say somewhere in the neighborhood of polynomial, but I'm really not sure on this one for now. So I'll leave it as a question mark, as an open question for now. But in any case, we know that sorting is O of n log n with quicksort. And since we probably won't beat that time with our algorithm, this is at best polynomial in this approach, right? We can do sorting for quote-unquote free in terms of asymptotic runtime. So this is somewhere in the neighborhood of O of n squared, or some other flavor of polynomial. So I think this is the sort of standard approach, and then we can see if we need to improve on it further later. But we're going to start by doing nums.sort. This is just a standard quicksort type deal. They want us to return it in a form of a list of lists. So we'll say val list of lists is equal to mutable list of list, which we'll take of type int. Then we can say nums dot for each. So for each number. And we'll have to grab the index too. So we'll use a for each index. If index is less than num size minus 2, I think. Then we can do var left is equal to num plus 1, var right is equal to num size minus 1. So the last index, and this is going to be our current index plus 1. We can say like while left is less than right, if nums at left, or we'll start with our main value, so num plus nums dot left plus nums right is equal to 0. Then we'll do list of lists, add a list of nums left and nums right. And then we can do left plus plus, right minus minus. And then at the end, after we do all that, we can return our list of lists. So pretty straightforward. Let me think if I missed anything. So we started by sorting. We created our result. We're going through each number. We have a pin here. We initialize our left at num plus 1. So this should be index plus 1. Sorry. Right. This should be our index, not our value. So our index plus 1. If index is less than nums.size minus 2, so we have at least two numbers to look at, left and right, respectively. One at after the index, one at the end. Then, actually, this should be less than num size minus 1 because we want to go at most in num size minus 2. Or wait, no, do we want to go to num size minus 3? Minus 2, minus 1. Yes, we actually do want to go to num size minus 2, or at num size minus 3, because our next value is going to be num size minus 2, and then our right side is going to be num size minus 1. So that actually, it should be less than num size minus 2. Then we just do our two-pointer sort of approach. We increment left and right. While left is less than right. And so on and so forth. Let's see. If I recall, there was also some other sort of shenanigans that we had to do. Let me just double check and toss in an example. So we'll start by sorting. So -4, -1, -1, 0, 1, 2, I think. 2, 3, 4, 5, 6. Yep. So -4, then we have these two. That doesn't work. Ah, right. Okay, so we also want to add a little bit of nuance to our two-pointer approach. So we can actually say when num plus nums, we can actually just pretty much do this entire thing. So when that happens, do that. If it is less than 0, that means that our number on the left is a little bit low, so we should do left plus plus. And conversely, if it's greater than 0, technically this could just be an else case. Alright, so if it's equal to 0, we add it to our list. If it's less than 0, so for example, -4, -1, and 2, right? So -4 minus 1, that's -5, plus 2, that's -3. That's a little bit low. So what we do is that we increment our left Same result here. Then we have -4, 0, 2. Again, continue. -4, 1, and 2. That's -1. At this point, left is equal to right. And then left is equal to right, and then we don't continue. We also want to make sure, let's see. We don't want to increment both. Or what I mean is that we don't want to increment both all the time. We only want to increment both when we have a match. So for example, -1, -1 and 2, that's fine. So we have a match there, right? -1, -1 and 2, that's a match. So now we want to move both. So -1, 0, and 1, that's another match. Okay, cool. And then after that, they cross, and then we can forget about it. So in this case, for all three of the cases, we will eventually encounter a situation where left is less than right, where they overlap, or where they are meeting, where they overlap or where they cross over. So in that case, again, we're taking this completely relies on the fact that our array is sorted. Otherwise, it would not work in that case. So we just do that. And then if it's less, we increment the left to try to increase the score. If it's greater than 0, then we want to move the right down to try to decrease our total. Let's see. So that seems correct now. And then 0, 1, 1. We start here, we start here, we start here, we grab it, it doesn't work. We move right down because it's too high, they overlap. Therefore we quit out, and this quits out, and we return an empty list. And similar thing for 0, 0, 0, but they cross over instead. So I think this actually does seem to work out. Let's give it a shot and let's see. Looks like we're missing a value somewhere. That's fine. That's fine. This is also okay. This is okay. This is not okay. We are missing a close bracket. So we want to return after we go through all of them. So little bit of bracket curly braces intrusion here, but looks like it's fine. Let's see. Looks like we did get a duplicate. Let's see why. Interesting. So we did this, -1 and 2. So that works. So then we move both, so -1, 0, and 1. Okay. And then -1 here also does. Maybe yeah. Okay, so we can't entirely do that because the pin also counts as a value. So how do we combat this? Index or num is not equal to nums index -1. So basically we only want to take the first value. We want to take the first value because the first value we have are the most possible choices. Here we only have our possible choices are sort of cut down because we don't have as many sort of numbers to work with. So we only want to deal with the first one, and the first one should automatically give us all of our answers. So our current number is not equal to our value before, so it should go through -4, -1, and not this second -1. I see. And let's see. If we want this to be the case, then we want index to be greater than 0. Or index is 0. So if the index is 0, then we're fine here. If the index is greater than 0, then this must hold. And that's sort of the condition that I've established here. It's a little bit messy, a little bit sort of obtuse, I guess. Or at least more obtuse than I would have liked, but it works. So it seems to work fine. Let's go ahead and toss in a submit and see if there's anything else we need to change. Looks like we have another issue here. I remember now. Okay, so if we have a match, we want to do while left is less than right and left is less than right and nums at left is the same, or nums plus 1 is the same as nums here. Basically, we want to skip over all the duplicates as well that are in our way, just so we don't deal with them. Left is less than right. Nums.right minus 1 is equal to nums at right. Yeah, a lot of cases to deal with duplicates here. Left is less than right and nums at right minus 1. I should probably wrap this, because I don't think that Kotlin will like it if I do a one-liner while loop. Let's see, so left is here, right is here, that works, okay. And then while the next value is less, or is the same here, is the same as the one that we're at. The one here is the same as the one we're at, so we move up. And then when they cross there, then we want to do another one just to go over, because this is basically we skip over all the duplicates and then we need to do our normal iteration. So I think that is how we handle that case, if I recall. Let's see. So that still holds, that still works for those. 0, 0, 2, 2. Let's give this a shot. Lots and lots of edge cases and corner cases to think about in this one. Gotta be real careful. Especially, it's just mostly around the duplicates, though. Let's give this another submit to see if I missed anything else. Okay, cool. Runtime is 71.94% submissions. Memory usage 67%, so pretty standard sort of submission type deal. I'm gonna actually do a quick check to see what this summation actually amortizes to. I'll be right back. Okay, so according to this Stack Overflow response, it seems like it, because of math, my summation knowledge is very, very rusty, and yeah, this is something that something that I do need to brush up on maybe. But at the same time, I feel like a lot of the LeetCode stuff is just it's very similar patterns. You see the 1 plus 2 plus 3 all the way up to n. That's just n, and it's very similar sort of result. You get a polynomial time. So this one, it seems like ultimately you get something of the sort of O of n squared time. So this ends up being O of n times O of n squared. And this is like that, plus O of n log n for the sorting. And that is equivalent to just O of n cubed. So this solution O of n cubed runtime, it looks like. Main lesson here is just two-pointer approach, but also huge amount of corner cases to think about. Or not necessarily huge amount of corner cases, but just corner cases to worry about. And that seems like that's a pretty standard pattern among medium questions that I've noticed. They do often take the simpler problems and just make it so it's not as easy to just implement it. Right. So for example, this one, it's like, okay, you know that it's a two-pointer approach to find the summation after you pin a number. However, there's a little bit of nuance when it comes to finding unique entries, right? And you need to do a little bit of additional sort of checks in order to make sure that you're not adding duplicate numbers. As well as the idea of using a sort, because in the case where your solution is going to be a polynomial time regardless, then you might as well see if you can get some additional information out of sorting your data if possible, because in the long run, in the world of big O notation, having that additional sorting time of O of n log n really doesn't matter that much if your solution overall is still polynomial. But in any case, I hope you learned something, and I will see you for the next problem.